Okay, let's get started. Any questions about last class? So let's recap a little bit. So before we recap, what are we going to do today? We are going to continue to talk about fluctuations, which is averages and variance and things like that. And I will show you that the fluctuation relative to the mean goes to zero, which is really fundamentally important. We'll show you how to get entropy and through that the Helmholtz free energy from Q. And then I will try to connect Q with omega, which is the connection between both partition functions. So before I go further, I want to make one point, which is many of you who have taken StatMech in undergrad have probably not seen this way of deriving the ensembles. And it might seem to you this way is less rigorous, but actually it's more rigorous. And this way, the way we did, which is to think about, when we were thinking about an NVT ensemble, we think about a system which maintains constant number, volume, and temperature by exchanging energy with a much bigger bath. That was the idea, right? And together everything was insulated. And this simple idea then allowed us to treat the system plus bath as a microcanonical ensemble. We could do Taylor expansion, and we were able to show that P nu, probability of a microstate, is e to the power minus beta E nu. This is not the only way it can be derived. This approach that we did, and we will keep doing for other ensembles, really goes back to Gibbs. This is how Gibbs did it in early 19th century or mid 19th century. In 20th century, people started using another approach, which is this entropy maximization approach that became popular around 60s or 70s after someone known as E.T. Jaynes. And that approach, in a sense, seems more rigorous because you don't have to write anything, you don't have to say anything, you just do the math. And you think, oh, this is more rigorous because there is just all math. But actually, it has more approximations. You are assuming a form for the entropy function. And that's not obvious at all. Furthermore, and we can talk more about that. And if you have the book by Macquarie, that's how Macquarie does it. There are further approximation, open questions there. So this approach is, in my view, and in the view of other experts in this department, is that this is a nicer, cleaner approach. So in this, what did we do? So we wrote down that, well, P nu is not this. P nu is 1 over Q multiplied by this, right? P nu is proportional to that thing. And Q is defined so that summation P nu should be equal to 1. That means that Q must be equal to summing over all microstates e to the power minus beta E nu. And this Q is a function of N, V, and T. T or beta, whatever you want to write. So this is known as the canonical partition function. And just like in microcanonical, we showed that omega of NVE carries thermodynamic information. And furthermore, by differentiating omega of NVE, you can get other thermodynamics out of it. Similar results apply here. For example, even though the energy fluctuates as per this relation, and we will come back to this relation and talk more about the energy today in a bit, it means the energy can take different values with a probability distribution. So the question is, what is the average value of the energy? That is given as summation over all microstate, probability of that microstate multiplied by the average of, multiplied by the energy in that microstate. And this came out to be minus partial log Q by partial beta at constant NV, which is the same as plus KB T square partial ln Q by partial T at constant NV. You will not remember these expressions. Maybe by the end of this course, you will remember, but you don't have to. Even if there is an in-class exam, you will have a cheat sheet, and this is the type of equation you write there, right? The thing that you need to remember is log of Q contains thermodynamic information. Derivatives of log of Q contain thermodynamic information about averages. Second derivatives of log of Q contain information about fluctuations. So we showed that the deviation from the average energy, if you look, which is known as the variance, this thing is the double derivative of log Q with respect to beta. In your homework, there is a third moment, or maybe fourth, I don't know what I gave. Enjoy, you have a lot of fun. It will be purely, it will be like type 2.5 fun. There's nothing nice about it, but it's important. And it gives you a perspective of going through that math. It helps you remember things a bit better. And this turned out to be plus kBt square CV, right? And this is a very interesting relation. You're talking about fluctuations in something at equilibrium. And how is it related to CV, which is what, how did we define CV? CV was, the truest definition of CV is delta Q, because Q is a path function, right? So CV, the truest definition is delta Q by T at constant V. That is a path dependent property. And that is related to something without doing any experiment. You can just study it by observing fluctuations at equilibrium. So it's a really nice equation. So we will spend some time looking at this equation and try to analyze it a bit more. And again, if something is not clear, just stop me. So the variance of energy is plus kBt square CV. That's what we are going to start with. So what we want to understand is, how do these things behave? How does the variance of energy behave in the thermodynamic limit? How does this behave as n tends to infinity? That's what we want to understand. So let's look at all the terms on the right side. What happens to kB as n tends to infinity? It's constant. What happens to temperature as n tends to infinity? It's constant, right? It's an intensive parameter. What happens to CV as n tends to infinity? It changes. It's not specific heat, right? It's the total heat capacity. How does it change? As a function of n, it's order of n. It's an extensive thing, right? If you have double the amount of coffee, you have to give twice the amount of heat, right? In the thermodynamic limit. If it's small, then things could be funky. So as n tends to infinity, CV tends to infinity as n tends to infinity. And it's order of n. It's not order of n squared. It's linear in n. That's the definition of an extensive quantity. What does this mean for us? This means that the variance of energy also behaves as order of n as n tends to infinity. Now that's very interesting, because this means that the standard deviation of energy, which is the square root of variance, goes to infinity as n to the power 1 by 2. That also diverges. Standard deviation also diverges, but it's a bit slower. It goes as square root of n. Why is that very interesting? Because anytime you have some measurement, let's say you are measuring some quantity Q or versus time, right? And you have something like this, right? Or let me make it something which we see. My wife is a geologist. I always make fun of papers written by geologists because they fit a linear thing to anything. I'm like, wow, it's a linear profile. Don't tell her I said that. So if this is something, so this is a plot in geology, okay? And they will say, oh, that's a beautiful linear profile. You fit something like this. Okay, fine. But how about this one? Why is this one a worse linear profile than the top one? Because the noise to signal is higher in the second one, right? There's so much noise. Instead, if you had something like this, then sure, it's a very good linear profile, right? Because the noise by signal has now gone down to 0. So what do I mean mathematically by noise by signal? Noise is the standard deviation, while signal is the mean. That's the idea. This is how one measures, not variance over mean, because variance has square of the dimensionality, right? Noise by signal is a dimensionless quantity. You are sitting in front today.
Yeah, the left-handed bench is in front.
Oh, I see. Interesting. He's there. This is chaos. So standard deviation by mean measures noise by sigma. And what is this telling us? So we just showed that the variance in energy goes as heat capacity, which is order of n. Therefore, standard deviation of energy goes as square root of n, right? So therefore, standard deviation of energy by mean of energy, how does this behave? Numerator behaves as square root of n, and denominator behaves as n. So what does the total thing behave as? N to the power minus 1 by 2. This is this 1 over square root of n. Therefore, the standard deviation of energy by mean of energy is order of 1 over square root of n as n tends to infinity. This 1 over square root of n shows up in equilibrium statistical mechanics all the time. It just, huh?
Go back to
Say. I'm dividing, that's where it came from. I want to look at noise by signal. Signal is the mean. I want to look at standard deviation by mean. The point being, it's really simple. Think about it. So I'm telling you that my system has an average energy of 1 kilojoule, okay? And I am telling you the standard deviation of this energy, it is 0.2 kilojoule, just some number, okay? You did an experiment and you measured the energy, how it changes as a function of time. Now I make the system 10 times larger. How much do you expect the average energy to look? 10 times larger. It's an extensive quantity. If you are in thermodynamic limit, it should be 10 kilojoule. How much will this quantity change? Standard deviation of energy. I just told you it behaves as square root of n. So if I increase something by 10 times, should this become 2 kilojoule or smaller? Smaller. What is the square root of 10? Approximately 3, right? So this will become something like 0.6 kilojoule, right? So it increased. Now let's make it 100 kilojoule. When we make the system, so n, let's say n is here some thermodynamic limit. So I don't know, 1 mole, 10 mole, 100 mole. As I do this experiment, when I make this much 100 times larger, this thing has to become 2 kilojoule, right? So notice now if you look, so the standard deviation is becoming larger and larger. That's true. But the thing that matters is if you were to report 1 kilojoule plus minus 0.2 kilojoule, that's a significant error, right? But if you were to report 100 kilojoule plus minus 2 kilojoule, that's less of a significant error. Why? How much, what percentage is 0.2 of 1? 20%. What percentage is 2 of 100? 2%. As you go to very, very large numbers, let's say you go to 10 to the power 4 kilojoule, this thing is going to become, so we multiplied by 10 to the power 4. So this thing is going to become 200 kilojoule. Again, the error has gone up. But now if you look at 200 divided by 10 to the power 4, multiplied by 100, how many percentage is it? Oh, I did something terrible here. You see my point. This may not be too much math. Yeah. So let me just write it down in the right-hand column here. Standard deviation of energy divided by mean of energy. How much is it? Here it is 20%. Here it is 6%. Here it is 2%. Here it is even smaller, right? So the key point here is if I plot the standard deviation of energy by mean of energy, it behaves as 1 over square root of n. It becomes less and less important. And this is of fundamental importance, right? Because what happens to 1 over square root of n as n tends to infinity? It goes to 0, right? Which means that if you are looking at an NVT ensemble and you allow n to go to infinity, then energy will almost all the time be the same as the mean energy, right? The fluctuations will become irrelevant. So let's plot this. What I'm trying to say here is if I, and I want you to pay attention here. And in this class, normally I don't have to do that because you guys are all quite alert on everyone, guys and ladies and everyone. If I plot the probability of observing an energy versus E, for finite system size, it's going to look something like this. And we will get back to the nature of the curve in a moment. As you increase the system size, it will start to look like this. And eventually, as you, actually, I should make it, I should worry about the normalization. So for finite system size, it's going to look like this. As you make the system size smaller, it will become tighter and tighter as n tends to infinity. In fact, at the very end, it will just look like a delta function, which means is that what this means is as n tends to infinity, even though E fluctuates in NVT ensemble, it is really close to E bar almost all the time. So we just got a sense that why, therefore, the NVT ensemble kind of starts to approach the NVE ensemble. Even though you're allowing the energy to change by fluctuations to happen, on an average, it's going to stay almost the same. Okay? Is this clear? Alex is dying to raise his hand. Why did we get this curve? Because we wrote down something else the last time, right? Think about this. P of E nu versus E nu. We derived something else for this. We derived a Boltzmann probability, right? We showed that P of E nu goes like this. So why on earth did I draw a Gaussian over here? How do I explain this? So this argument is fine, right? We just showed, we calculated the variance and we showed the standard deviation is square root of n. Therefore, standard deviation divided by mean is 1 over square root of n. This is fine. We did not say anything about the nature of the curve, right? This could have applied to any probability distribution. But here, I just made one more assumption. I drew something that kind of looks like a Gaussian. Where did that come from? Can anyone help me here? How did I go from this curve to this curve? Huh? Yeah, exactly. Kinjal is exactly in the right point. So we are talking about P of E. We are not talking about P of E nu. Okay. P nu is the probability. This is subtle, and Chandler kind of talks about it, but in his peculiar style very quickly. P nu is the probability of a microstate. But in order to calculate P of E, you have to look at two things. P of E is going to be proportional to e to the power minus beta E, but it is also going to depend on the number of microstates that you can have with that particular energy. Okay, so there's a convolution of two things. There is a product of two things. So P of E nu goes down exponentially, while omega of E goes up like this. And if you look at their product, that's how you get a Gaussian. Why does omega of E go up in a concave manner? If omega of E went up in a convex manner, will this be true? If omega of E, let me redraw this. If omega of E was going up in this manner, would we have their product as a Gaussian? It won't. It will go to 0, right? So it's very important that so actually, I will just draw this. So this is not possible. What we really want omega of E to do is to go up like this in a very sharp manner. One moment. So their product now is going to look something like this. Go ahead.
Is it related to second law from dynamics?
Yeah, it's related to partial S over partial E, right? That's what we said. So when we said that if S is equal to KB ln omega, and if partial S by partial E at constant NV is going to be positive, this means that partial ln omega by partial E is going to be positive, which means that omega as a function of E must be something like e to the power omega, right? For example, I'm not saying it has to be e to the power omega, but something similar, right? Omega, since log of omega differentiated with respect to E is positive, if you take the log of something and it is still monotonically increasing, then the function itself must be really, really increasing abruptly, right? And this makes intuitive sense, right? The number of states a system can have and this goes back to the discussion we had on Slagen in class, right? I mean, there is a reason why I put omega of E as 0, as E tends to 0. This relates to the ground state in quantum mechanics being degenerate. Yeah, you could have some Hamiltonians where there's some degeneracy, but otherwise it's non-degenerate. The number of microstates at E is equal to 0 is 1. But as you pump energy into the system, the number of microstates increase, right? You can be arranged in so many ways. And not only does it increase, it increases very, very rapidly. So P of E is a product of these two things. It's a product of omega of E multiplied by e to the power minus beta E.
But in our derivation for the macroeconomical ensemble, we never use the SSKBL omega definition. We don't need it.
We don't need it, but in order to connect it to thermodynamics, we need it.
But that's a postulate, right?
That's a postulate. And this is where when I was ranting over the Macquarie approach and the Janes approach of getting ensembles, there they don't have to do this because there they say S is equal to minus pi log pi. That's their postulate. And they start from that. So one way or the other, you need to have a postulate. Our postulate is more connected to thermodynamics. This definition of entropy is what many textbooks assume, which is not obvious to me. Why this definition? Why not another definition? So our postulate is that this entropy function, which comes from the microcanonical ensemble, must be consistent with the laws of thermodynamics, right? And that leads us to this idea that omega must increase. So there is no new postulate.
So for the when we had to derive the expression for the Helmholtz energy, you said that we couldn't use E minus Ts directly because we don't know what the functional form of the entropy is. Yet here
now we will. We haven't gone there yet. We haven't. Yeah, this is exactly what we are going to do. So that's the next thing. That's the next thing. Good. Have you seen my notes or something? That's the next thing we are going to do. So the point here is, so let me recap just a bit. So standard deviation of E by mean of E goes as 1 over square root of n as n tends to infinity. More generally, you will see this in statistical mechanics, that standard deviation of extensive quantities divided by mean of extensive quantity, that same extensive quantity goes as 1 over square root of n as n tends to infinity. This is really powerful, generic, it shows up all the time. It really shows up due to central limit theorem. That's the mathematical reason behind it. But it also means that as you get to n tends to infinity, statistical mechanics converges to thermodynamics, right? Thermodynamics, we didn't talk about fluctuations. We just had average quantity. We said, what's the energy? That's it. So statistical mechanics, equilibrium statistical mechanics at least, converges to thermodynamics as n tends to infinity.
Why do we ignore all the stuff in the middle?
What is in the middle?
Like you say, you're increasing by a scale of 10, then 100, then 10 power 4, then you go to infinity eventually.
No, we never ignore it. You can always do it. You will do it in the homework, don't worry. I ignore it, but not you. So this is one thing to keep in mind. The other thing to keep in mind, which is a bit more abstract, is that the probability of finding a state with a certain energy from a canonical ensemble, it's really a product of two things. It's a product of omega E multiplied by e to the power minus beta E. Okay, and this goes to how we did the derivation. Remember, we had a product of two things and we said one is smaller than the other one. That's what we are writing over here, right? That's how we derived the canonical ensemble. And omega E behaves like this with energy, while e to the power minus beta E behaves like this with energy. So when you take that product, you get something that P of E behaves as a Gaussian. And as you make the system size larger and larger, this Gaussian becomes tighter and tighter. So what does this mean? This means that in thermodynamic limit E, thermodynamic limit for a NVT ensemble, E approaches E bar, okay? The fluctuations with relative to E bar that you're seeing in the E becomes smaller and smaller and smaller. It's not that the fluctuations go to zero. The fluctuations, the standard deviation keeps getting bigger and bigger in its own magnitude. It's when relative to the energy, right? Error of 200 kilojoule is really bad if your mean is 1 kilojoule. Error of 200 kilojoule is kind of nothing if your mean is 10 to the power 4 kilojoule, right? That's the point over there. Go ahead.
So is there a scope for why it's a motion?
Yes, we are not going to do it here. Remind me on Slack. I will prove it. You can be, and that's one of the Chandler exercise problems. Maybe I should have given it in the homework. You can do that, and you have to use central limit theorem. That's where it comes from. So you are observing a lot of energies, right? And you're doing independent observations. And central limit theorem says that if you're making lots and lots of observations, their mean behaves like a Gaussian, right? That's the point. So it's effectively just central limit theorem. Okay, I don't want to get into that in this course. Good. So this means that energy in a canonical ensemble behaves as E bar. In NVE ensemble, that's a given, right? In VE ensemble, we have fixed the E. So there is no problem. Here also it does that. So now let's use this to think about the Helmholtz energy in a canonical ensemble, in NVT ensemble. We want to think about is in thermodynamic limit. So in thermodynamic limit, we can say we are going to use instead of E bar, right? Because we have reached a very, very large system size. E is going to be approximately the same as E bar minus TS, okay? So E bar we have calculated. Let's now think about TS, or specifically S. So S is going to be KB ln, and this is where some of you are going to take out your swords and go at me, not rigorous, not rigorous, but if you think about it, it's actually very rigorous. As we reach the thermodynamic limit, S can be written as KB ln omega of E bar, right? And this is, I will put a star here because this is subtle, but if you think about it, in thermodynamic limit, this is exact. Right? The energy has become constant. If the energy is becoming constant, we can use that the S is then connected. So we are exploiting here that the canonical ensemble becomes the microcanonical ensemble in very large system size. Okay. So S can be written as KB ln omega E bar. This is confusing. The first time I read this, I was like, wait, what are you doing? This is also terrible. Okay. So stay with me. So we have to think about omega of E bar. Remember how we defined the probability of observing a certain microstate in microcanonical ensemble? What was the probability? It was 1 over omega of E bar, right? Every microstate is allowed. And if you have omega number of microstates, P is equal to 1 over omega, right? So, oh, I should start numbering my equations today. This is equation number 1. This is equation number 2. This is equation number 3. So put 3 in 2. Then S is equal to KB ln 1 over P of E bar, right? And what is that? That is minus KB ln P of E bar. So it's kind of like a magical proof almost. Now we will use the fact that P of E bar we can take from a canonical ensemble, right? So what is P of E bar in a canonical ensemble? That is e to the power minus beta E bar divided by the partition function, right? So S is equal to this one. This is equation 4. Therefore, equation 4 can be rewritten as S is equal to minus KB ln of e to the power minus beta E bar minus KB ln of 1 over Q. Okay? Everyone happy with that? What does this become? Ln of e to the power minus eta E bar. What is that? That is just minus beta E bar, right? So this becomes KB plus beta E bar. And this becomes plus KB ln Q. Now we are getting somewhere. This becomes S is equal to KB. What is beta? That is 1 over KBT E bar plus KB ln Q. KB cancel. T can be taken to the left side. This becomes TS is equal to E bar plus KBT ln Q, or E bar minus TS is equal to KB ln Q. And that's what we wanted to show. Correct? So no two lines in this proof on this page are mathematically complicated, but there are a couple of subtle physical approximations. Let me mark them. Here we are using microcanonical ensemble, while in this line over here, we are using canonical ensemble. In the same proof, we used both. Right?
Should it be KBT and Q?
Oh, yeah. Okay. And Chandler goes through this proof, I think. E bar minus TS is equal to minus KBT ln Q. And what is E bar minus TS? That is average value of the Helmholtz free energy in thermodynamic limit. So let me go to next page. I'll just wait a moment. So we have just shown that E bar minus TS, and you can call it S bar if you wish, in the thermodynamic limit, is equal to minus KBT ln Q. And what is E bar minus TS? That is Helmholtz energy, right? That's the definition of Helmholtz energy. So we have just shown that A is equal to minus KBT ln of Q of NVT. So that's our connection of canonical ensemble with thermodynamics. And this is very similar to S is equal to plus KB ln omega of NVE. And you can see how the natural variables are preserved. A is a function of NVT. S is a function of NVE. Natural variables are kept, right? So this now opens up our pathway of using the canonical ensemble. If we could calculate, and you have all the homework is full of problems, and this homework is going to be tough, okay? And as it is written in the syllabus, this homework will lead to many groans like, oh, I don't know how to do it. See, he's already groaning. Because the ideas are there, but you have to apply it. You have to set it up a little bit. In this homework, all you will be doing is to either calculate Q or calculate omega and then differentiate it many, many times to calculate lots of things. And you will see how it really works out. I'm going to work through a practical problem doing that. I'm doing it deliberately in parallel to your homework, because I shouldn't say to make your homework harder, but to make it more useful for you. Okay, so work through it. There is a bonus problem, so you have the opportunity to score more than 100. So now if I asked you, great, you have some problem where you set it up in a canonical ensemble, you calculated the canonical partition function. Tell me the pressure of the system. What would I do to do that? How would I get the pressure from a canonical ensemble?
Derivative in terms of volume.
Yeah, do you remember what's the relation?
It's dA over dV.
You're the only one who remembers things like this. The good memory. I always forget. There's a minus sign though.
Yeah.
And if you are caught in a debate on a stage and you have forgotten this derivation, what would you do to derive this very quickly? Start with the fundamental equation. Oh, you guys are learning. That's awesome. TdS minus PdV plus mu dN. Anytime you forget, you tell them, give me a blackboard. I will derive anything you want. Okay, this is just like my organic chemistry textbook by Morrison Boyd says, if you are stuck on an island, the only chemical you should have is ethyl alcohol. And from that, you can make every possible chemical in the world, and you can also enjoy ethyl alcohol as you're making the chemicals. But this is the ethyl alcohol of thermodynamics and statistical mechanics, okay? From this, you can create everything. For example, you can write down dA is equal to minus PdV minus whatever it is, and get the relation. So P is minus partial A by partial V at constant NT, right? And we just showed that A is equal to minus, let's give it a name. We should call it equation number 5, right? So therefore, P is equal to KBT partial ln Q by partial volume at constant N and T, right? So if you have calculated the canonical partition function, you can calculate all sorts of thermodynamics out of it. You can do the same. We showed how to get P out of S also, right? Last time we showed that. So you can get pressure out of microcanonical ensemble. You can get pressure out of canonical ensemble. It's up to you. Which way do you set it up? Okay. And the point, in order to derive this, we really made use that in the thermodynamic limit, we can kind of move back and forth between canonical and microcanonical ensemble. Any questions? So remember these two. I want to look a bit more carefully at the connection between canonical ensemble and microcanonical ensemble and show how the partition functions are actually just like these two things in thermodynamics, where Legendre transform of each other. Is there such a relation between Q and omega? That's what I want to show next. It turns out Q and omega are Laplace transforms of each other. So let's look at it next. So just like the simplest transform that I can think of, which makes intuitive sense to me, is a Fourier transform, right? And the thing about a Fourier transform is you can Fourier transform a function. You don't gain any information, right? You can look in the Fourier space, it is the same information. It's sometimes beneficial to look in the Fourier space, right? So when you're doing a molecular dynamics code and you have Coulomb interactions in a system, Coulomb interactions decay very, very slowly, right? If you have read any books by Feynman, he talks about it, right? The self-energy of an electron is infinite because it keeps going slower and slower and slower. But if you look in reciprocal space, it decays very, very quickly. So there is advantage in looking in Fourier space or in inverse Fourier space. Similarly, Legendre transforms, there is advantage looking in one space or the Legendre transform space. The physics that you get is not different. The physics is the same. Same thing applies to Laplace transforms. And let's look at that next. So we are going to look at, what are we going to do this? Connection between omega and VE and Q and VT, okay? On next page. So how to do this? Let's start with Q and VT. What is the definition of Q and VT? Go to every microstate and calculate e to the power minus beta E nu, right? Or go to every microstate and calculate e to the power minus E nu, which is now a function of N and V divided by KVT. What I'm going to do next is not just to show you some elegant connection between the Laplace transforms, but pay attention to the next step. This will show up many, many times in the course of this semester. It will help you in many problems also. Here, I was summing over all microstates, right? What is a microstate? A microstate is an arrangement in phase space, right? It's something complicated. I want to write down this summation, not over microstates, but over all energies. So it's a change of basis, right? And we did this. That's how we calculated our Gaussian curve, which we showed, right? That it goes. So in order to do this, I have to do two things. First, I have to account that in a given energy value, I will have E divided by KBT. But now I also need to account that a given energy value will have many possible microstates associated with it, okay? So this change is super important. We switched from microstates to summing over energy. Is this clear?
Can you clear how you switched?
Okay, so what is a microstate? a microstate is a given location in phase space, right? You have to specify everything in this 6 n dimensional space. And if you're doing that integral in that 6 n dimensional space, you go to the energy in that little box in phase space and you calculate that. So in this one, you are going to phase space and calculating in every little box of phase space, you are calculating the value of the energy in that little box and taking its exponential, right? That's what we did over here. But here, and also furthermore, this is very, very high dimensional. P goes from 1 to 3n, R goes from 1 to 3n. Here I am saying, no need to worry about all of that. Go to a one-dimensional space and calculate the probability in that space. Do this integral in one-dimensional space. In this one-dimensional space, you have to understand that every possible value of energy is actually coming from omega E contributions, right? So when you go from this 3n dimension, 6n dimensional space to a one-dimensional space, you are taking lots and lots of boxes which had the same energy and compressing it into one line, right? This line is ignoring the information that in very, very high dimensional space, this has some energy, this has some energy, this has this energy, this has that energy, right? All these possible arrangements have the same energy. Ethan is on Zoom. Ethan, I was moving my hands very vigorously and saying that all possible arrangements of my hands have the same energy, but there are many, many different arrangements, right? So those number of arrangements is omega E. So as you go from a very high dimensional integral or a sum to a one-dimensional sum, you have to account for this degeneracy. So this is just one moment. So this omega is known as the degeneracy of energy E or the density of states. So this density of states idea keeps up coming more and more. Go ahead, Nick.
I was going to ask, so is this, I guess, conversion or transformation that we're doing, like unidirectional to meet backtrack? or-
Backtrack also. You'll be doing it both with, absolutely. Absolutely. So this is abstract. China talks about it just a little bit, but so it's good that you asked me to explain. Hopefully it's clear now. So we went from microstates, which is a very, very high dimensional sum, to energy, which is a one-dimensional sum, right? And anytime you go from very high dimensional sum to a low dimensional sum, you have taken a lot of information with the high dimension and compressed it to one value, right? And that degeneracy is omega of E. So let me write down what we have so far once again. So I have just showed that Q of NVT is summation over E omega of NVE multiplied by e to the power minus E by KBT. While this omega NVE in this case is really the degeneracy of E. Right? So if you were a ground state, omega would be 1. There is only one microstate that leads to that ground state, right? For well-behaved quantum mechanical systems. So we can write it down. Those of you who like quantum mechanics, in quantum mechanics, when we sum energy, we think about energy levels, right? So let's say if you knew the energy levels of a system, you could write it down as summing over all energy levels, calculating omega for that energy level, and multiplying by e to the power minus beta EL. That's what we are doing over here. So as n tends to infinity, this summation becomes an integral. And what equation number is this? This equation number 6, I don't think. Yeah, equation number 6. Equation number 6 becomes Q of NVT tends to an integral dE 0 to infinity. Energy can go from 0 to any infinite value. Omega of E to the power minus beta E. This is a Laplace transform. This is the definition of a Laplace transform. So we have just shown that Q NVT, and I should be rigorous here and write down omega NVE. Q NVT and omega NVE are connected through a Laplace transform. And anytime you have Laplace transform, you have the same physics. It just might make sense to you to work. Your physical conditions dictate which partition function you work with, right? As we go to applied problems, so we have to do only one more ensemble after this, which is when we allow number also to exchange. After that, everything is just application. of different types. It will look like theory, but it's really just application. The basic physics is done. In fact, the basic physics in Chandler does the grand canonical ensemble in half a paragraph, but you will take a bit more time to do it, because, yeah. So, but the basic idea is the same. Instead of a bath where energy is exchanging, now you allow number also to exchange. Instead of doing a 1D Taylor expansion, you do a 2D Taylor expansion. The same idea. But the physics is the same because a Laplace transform for any function does not add any more information to it. It's a choice of basis in which you're working with. Either you are working in a high dimensional microstate or you're working in an energy basis, the physics is the same. Okay, you're working in NVT or you're working in NVE, the physics is the same. Any questions? Yeah, go ahead, Patrick.
Why can we identify the omega NVE in the last line or a couple lines up with the microcanonical partition function when in this case the energy is fluctuating and it's not the complete system, it's a subsystem.
Yeah, good point. So that's because that's a very good point. So here I'm not even making a thermodynamic limit approximation. This is what I did over here is exact, because what we are saying is if you had a fixed energy of the system, how many microstates would you have, right? That's what we are talking about. If you had a fixed energy of a system, how many microstates could the system take? And that is a microcanonical ensemble, right? Microcanonical ensemble talks about fixed energy. That's why we can do it, but very good point. Otherwise we couldn't do it. So we are looking at energy at a time. We say, okay, you got energy 100 kilojoule. If you are fixed at 100 kilojoule, how many microstates could you have? And that's what microcanonical ensemble does. We used something very similar to this in last class also. If you go and see in the notes, you will see that I did something very similar to this. Okay. So now we are moving at a good rate. It looks like a fast rate, but it's actually a good rate. I won't call it a super fast rate because now this is my 5th time teaching this course. So I would say this is somewhere in the slower rate. The first time I taught it, it was way faster. Poor students. Okay, so this is all abstract. I want to look at a practical problem. It's practical, quote unquote. I will set it up, but I will actually calculate Q of NVT, omega of NVE, and show you how things are actually the same. Just to say that, oh, they are the Laplace transform, therefore they have the same information. That's fine. If you really love Laplace transforms, this makes you very happy. But if you're like me, then you're like, I don't know. So let me write down. So we just showed that Q NVT and omega NVE are Laplace transforms. I posted a PDF article on the course webpage, which I actually shared last semester also. It's by Royce Zia. Does anyone know who is Royce Zia? Archipel Zia? He's a professor here in physics. He's now emeritus or something. And he was very passionate, or still is, over the last like 4 decades about teaching physics in a simple manner to undergraduates. So he has articles in American Journal of Physics and things like that. And this article is by him, which really talks about Legendre transform in thermodynamics and Laplace transform in statistical mechanics and connects both of them. So now is really a good time to go and read that PDF article. You will enjoy it. It connects everything together. It's a beautifully written article. Even Chris gives it in his non-equilibrium statistical mechanics class. He gives that article as Chris Jarzynski as a suggested reading. So it's one of the best articles out there on connecting why is it that we get Legendre transforms in thermodynamics and Laplace transform in statistical mechanics and joining the dots over here. So it's all kind of beautiful. But what I want to do now, okay, so I want to mention here, read article by Zia on, well, actually I said something wrong. Zia is a professor at Virginia Tech. Joe Reddish is the professor at Maryland. Does anyone know Joe Reddish? Okay, so I didn't make much of a mistake. So yeah, they are both senior professors who wrote this paper together, Zia and Reddish, on course webpage, which talks about all this. It's not going to be on the exam, but it's useful to read it for your own appreciation. Okay, excellent. So now let's look at an illustrative problem. For this illustrative problem, I will ask you a couple of questions and I want you to give me the intuitive answer. And then I will show you how both ensembles give you the same intuitive ensemble answer through complicated math. For first of them, we are going to use our formula for permutation and combination. For the second one, we are going to take summations into products and products into summations. So very complicated way, you will get the same limiting answer as intuition suggests, but you will get a much more, you will see why it's powerful. So this is the problem. We have n particles which are distinguishable. Okay? What does that mean? What's the name of that Korean show on Netflix? Swimming knows, where everyone got killed.
Squid Game.
Squid Game. Do you like that one? No, she doesn't like it. She's a great expert on Korean TV shows, right? So if you need any advice, you can ask her. So in Squid Game, all the participants are distinguishable, right? But all the people who are killing them are indistinguishable, right? So we are not talking about the people killing them. We are talking about the participants, okay? And this distinguishable, and so think about Squid Game. If you're just reading my notes later, you're like, what the hell was he talking about? So they are distinguishable Squid Game participants. Later, we will look at the Squid Game operators who are indistinguishable, and we will make corrections on how to deal with it. So furthermore, they are independent. They behave completely independent of each other. Is that true in Squid Games? No, not really, right? So, but we make that assumption over here. And the third thing we are going to say is every particle can be in one of two states with energy 0 or epsilon. And epsilon I'm going to put more than 0, some non-zero value, okay? So how is this going to look like? What I'm trying to do, if let's say if I look at particle number 1 and I draw a box over here, and particle number 2, and I go to particle number n, I can draw something over here. And this is when the energy is equal to 0. This is when the energy is equal to epsilon. And I will denote every particle with a little star, okay? So this one, let's say it can be in energy, higher energy state. Maybe this one can be in lower energy state. Maybe this one is lower energy state. This one is high energy state. Even though I am using star to denote all of them, I'm still calling them distinguishable. Why? Because of this label, right? I'm saying this is particle number 1, this is particle number 2, this is particle number n. If it was indistinguishable, I won't be able to sort it like this, okay? Is that clear? So if it was indistinguishable and I had an arrangement where first particle was in top and the second particle was in bottom, that would be the same as the arrangement where first is in bottom and the second is in top, right? In our case, these two are not the same, they're distinguishable. So here's my question for you, and you have to answer it intuitively. At 0 temperature, what do you expect the average energy of this system to be? And similarly, at infinite temperature, what do you expect the energy of the system to be? Let's start with 0 temperature. What should happen? Go ahead. Why?
Because
Huh?
the way it's just
It's intuitive. Yeah, everything goes to ground state, right? And there is a unique ground state. Everything comes and drops in the bottom, right? At 0 temperature. So at 0 temperature, you expect this to be 0 intuitively. At high temperature, infinite temperature, what do you expect it to be? N epsilon over 2. Not n epsilon, but n epsilon over 2. And this is very important because the temperature is so much higher. This temperature is such that the value of Kb multiplied by T is much more than epsilon. So whether you are in 0 or in epsilon doesn't matter. You're just boom, 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 right? It's like, Like he had a lot of Red Bull, right? And he's just jumping around back and forth. Sometimes he's on ground floor, sometimes he's in first floor, sometimes he wants to just fly from the top of the building, but he can only be in ground floor and first floor, right? He's just going back and forth. Okay, so on an average, he will be somewhere in the middle, epsilon/2. And this is true for all n particles. So this is what we expect intuitively. Now we are going to show that how microcanonical and canonical ensemble give the same result. Furthermore, they also tell you what happens in finite temperature in the middle. And it's really, really nice. Okay. And once I do that, I will show you how to correct it for indistinguishable particles and things like that. So we are going to spend time in this. And as you work through your homework, this will become more and more clear as to why we are doing this. By the way, no class on Tuesday. Okay, everyone remember that. Don't come here on Tuesday. I mean, you can, but I don't know what you will do. You can hang out, you know, do your homework together or something like that. Oh, I want to see. I want someone to tell me if ChatGPT helps you with this homework. I strongly encourage the use of ChatGPT. Okay, so I'm different from other professors. And just tell me. I really want to see which problems do you think ChatGPT just did it for you. Okay, go and try. And I want to know. So we are going to solve this problem using two approaches. The first one is the microcanonical ensemble. Why can we use both approaches? Because the way I set up this problem, I didn't really tell you, you know, like, is it connected to a bath or not? I just showed you what can happen, right? So you can set up the environment as you wish. So in a microcanonical ensemble, we need to, first thing we have to think about how to write down the microstate of the system. So I told you earlier that the way to write a microstate is to go to phase space and kinetic energy and potential energy and things like that, right? Position and momentum. Here there is no position, here there is no momentum. Microstate is the most detailed microscopic observation you can make on this system, right? So here, writing down the microstate of the system really means going down to that box that I drew earlier and specifying which particle is where, right? This is one microstate of the system, right? This one is another microstate of the system, right? So these drawings are, for example, one way to, yeah, go ahead. We'll get there. So, but how to write down the microstate of the system mathematically? How should we do it? So we can write down the microstate mathematically by writing a set of binary numbers. So for this picture over here, I would say that the first particle is in the higher energy state. So let's call it a 1. The second particle is in a lower energy state. Let's call it a 0. The third particle is in a higher energy state. Let's call it a 1. The third one is a 1. The fourth one is a 0, right? For this one over here, how does it look like? 0, 1, 1, 1, 1, right? This, if I write down a long binary number like this, that is the microstate of the system. And it's going to be unique, right? The same binary number cannot correspond to two microstates because in this system, there is no other information. The microstate is which energy level you are in, period. Okay, so my microstates will basically look like 0, 1, 1, 0, 0, 0, 0, 0, 1, something like this, you know. So first, second, and nth. I will have a bunch of numbers like this. Okay, good. So what do we want to do now? In a microcanonical ensemble, to get any thermodynamics out of it, we have to write down the microcanonical partition function. That's what we need to calculate, right? So we need to calculate omega of NVE. there is no volume here, right? Volume has been made redundant. We are not talking about volume at all. So in this case, this is going to be omega of NE, since no volume consideration. Now it starts to get interesting. What is omega of NVE? Omega NE. This is the number of microstates you can have corresponding to a certain energy E, right? So this is number of ways the system can have a total energy E. All right. What is the value of omega NE when E is equal to 0? 1. Does everyone agree? Which binary number does that correspond to? 0, 0, 0, 0, 0, 0, 0, right? So this is 0, 0, 0, 0, 0. How about omega of N? What is the maximum value of the energy we can take? N epsilon, right? Everything in the excited state. What is the value of this omega? 1. Which binary number is that? 1, 1, 1, 1, 1, 1, 1. So we know the two limits. Now we need to think about something in the middle. Okay, so I'll give a moment. We will go to the next page. Okay, let's go to the next page. I will write these two final formula right again. So omega of N E is equal to 0 is equal to 1, which corresponds to the vector nu is equal to 0, 0, 0, everything 0. And omega of N E is equal to N epsilon is also 1, because that corresponds to nu is equal to 1, 1, 1, 1, 1. What we are interested in is omega N E is equal to, and pay attention with the algebra here, M epsilon. Okay, something general where M can take the value between 0 and N, right? That is the range of the energy we can have. M can be 0, M can be capital N, right? And we want to calculate this thing. This is a counting problem. What does this mean? If, let's say, let's make it intuitive before we get into the math in the more general setting. Let's say I had 8 particles, okay? N is equal to 8. And let's say my M is equal to 4. So if I write down microstates now, I want to find out states with energy 4 epsilon, okay? So I want you to think and tell me, this vector 0, 0, 0, 0, 0, 0, 1, 1, is this a microstate consistent with energy equal to 4 epsilon? No, what is the energy here? 2 epsilon, right? So this is not permissible. However, 1, 1, 1, 1, 0, 0, 0, 0 is permissible, right? But that's not the only one. 0, 1, 1, 1, 1, 0, 0, 0 is also permissible. There are a bunch of them. And omega N, and for example, there is also 0, 1, 1, 0, 1, 1, right? 1, 2, 3, 4, 5, 6, 7, 8. These are all permissible. There's a bunch of them. So in this case, we are talking about omega N equal to 8 and energy is equal to 4 epsilon. How many microstates can we have consistent with this? How many ways can I put in 1 in 4 locations when there are 8 possible options? 8C4. Why not 8P4?
Because the arrangements are different.
Even though they are distinguishable, it does not matter which one did we give a 1 first, right? So this is 8C4. What is the value of that? 8 factorial divided by 4 factorial divided by 4 factorial. If this makes sense, then the general problem is trivial. So therefore, omega of N E is equal to M epsilon is N choose M, okay? Or N factorial divided by M factorial divided by N minus M factorial. This is the number of microstates. And And if M is confusing you, M is really nothing, but you can think about M as number of particles in excited state. So this looks like a toy problem. But if you're doing any quantum mechanics in your research, half the problems are addressable through this, right? You know the energy levels and you are just counting, right? And then you calculate all thermodynamics out of it. Of course, you don't have two states, you have more than two states, right? And it's another problem to calculate the separation of the energy levels, right? Quantum mechanics allows us to do all that, right? So, but this framework is super powerful already. Simple counting.
For distinguishable particles, will you always use a complement? Is there any case where you would use a permutation for distinguishable?
We will get to that in like enormous detail, don't worry. We will talk about, yeah. We will do the full quantum mechanical picture, and then I will show you as to why this was a cheating. That here we actually cheated. And what I did, even though I'm doing it for n is equal to 8, is applicable only for very, very large n. It will come. It will be a homework problem, which half of you will get wrong. And then I'll be like, aha, because you made this assumption. So I have to wait for it. So I just showed you that omega of n e is equal to m epsilon is equal to n factorial by, and what is the value of m? M is e by epsilon factorial divided by n minus e by epsilon whole factorial. I'm going to stop here. Next time, since we have this, now we can calculate S, right? We can do S by taking KB of ln omega. Once we have S, we can manipulate it to get our average energy, and you will see how it makes sense. So next time, on next Thursday, we will do this, and we will also do this for a canonical ensemble. And then I will do a third approach, which will finally give you a sense for why do we call the partition function as a partition function. And that will go to this n factorial business a bit more. So we are going, next Thursday will be all about this problem. And the way I derived this is going to help you in the second homework. I've deliberately made the second homework a bit advanced because I think it will help you work through it. Yeah, I know it's advanced, so I will be lenient in the grading, but it will help you develop an appreciation for what you're doing. Okay, so I won't see you Tuesday. I'll see you next Thursday.